Okay, Assalamualaikum and good afternoon. So I think we're going to continue with where we have left off. So essentially we're still in chapter 6. I hope to finish, chapter 4. I hope to finish chapter 4 by today. So we have to skip a few parts. So for your own self-read. Okay. Let me just go to the whiteboard. Okay, what we had previously was to look at applications of partial differentiation to what you call generally extremization problem. So let me just do that example again. So go back. So we have done, well, we have introduced this particular example. So let me just cut and paste that particular picture. Oops, not big enough. Let me do that again. Right, so let me just start over a little bit just to refresh your memory. So we are trying to do this extremization problem for this particular what you call example that has been worked out in the book. Okay, so let me just remind you. Trying to find where's my pen for the so let's recall what was the question previously. So what we did was to extremize, or in this case to minimize really the material for this kind of geometry. So this is essentially the length of the tan, and then the width of the tan given by this so-called isosceles triangle. So midway is actually gives you length W. So we have done this. So essentially the thing to be extremized is your area. So the area is given by, let me just work it out. Since we have done it, so probably I'll just write the answer. Oops. W, that's cosecant theta. So this we have, so these are going to be sort of minimized. Okay. And the volume is given by W squared L tangent theta. So we have done that, all of this before. So what we need to do is essentially to minimize this area, and the variable that is sort of written inside this particular equation of the area is your theta as well as your W. So essentially what we have was to differentiate A with respect to W. That was given before as 4W tangent theta minus 2V cosecant theta over W squared, and that has to be equal to 0 for extremum point or stationary point. and then the other variable is theta. So that the theta is going to be 2w squared secant squared theta minus 2v on w cosecant theta cotangent theta equals 0. From the first equation, so let's number the equation here, 1 and 2. So let me push this thing up. From equation 1, one could sort of do the algebraic manipulation here, so to get w cubed to be equals to 2v cosecant theta divided by 4 tangent theta. And then from equation 2, you have another equation for w cubed, which is 2v cosecant theta cotangent theta over 2 secant squared theta. Okay. So now we need to solve this. Well, we have two equations for w cubed, so you equate those. Equate w cubed. So that will give you some factoring out a factor of 2 there. So this will be 2 tangent theta equals to cos theta. So you simplify this, cos theta, or maybe I should also factor out your v. So let me also erase that. I have cosecant. No?
I'm really sorry for interrupting, but my friend is still waiting to get into this government.
Okay. Usually it's auto admit. I'm not sure why it doesn't work. Okay, never mind. So where will we? So we are equating these two equations for w cubed. Okay, so I think I should simplify this. Maybe I should erase everything. I will simplify all the equate w cubed and then simplify. I don't want that. W cubed. So we want to simplify this a little bit, so I'm just going to write down the answer. Cos theta over 2 sine squared theta. Is everyone coming in all right? Yes, possible. Okay, cos theta over 2 sine squared theta equals to, again, this is after simplification, cos theta cos squared theta divided by sine squared theta. Of course, you can actually simplify this further, but one of the things that we want to see is to make sure that we have a valid solution. So one of the solutions that we want to eliminate essentially is when sine theta equals 0 and cos theta equals 0. So we're going to eliminate these possibilities Why? Well, if you remember that was theta already, so let me try to draw this. Theta is this angle. Okay. So if theta, sine theta equals 0, that means theta equals 0, then it will correspond to this kind of 10. So everything is flat onto the ground, so which is not the thing that we want. Or if cos theta equals 0, that means it's going to be just this vertical thing. So this is again, it's not acceptable. Okay. So this is cos theta 0, this is sine theta 0. So we're going to eliminate those possibilities from this particular equation. Remember that this equation has already been extremized using the partial derivatives. Okay, so we need to find what would be the right angle that gives you this extremum or minimum 10 material. So if one looks at that equation, so I'm going to, since sine theta is not going to be 0, I can just divide by a sine squared theta from both equations. So we are left with half cos theta equals to cos cubed theta. Okay, or we can simplify this further. This gives you cos squared theta equals a half, or in other words, your cos theta is going to be 1 on square root 2, and that corresponds to theta equals to pi over 4. So really, this is what? This is 45 degrees, okay? So that would essentially minimize the material for the tan. Right. Okay, there are, one could also try to solve a few other things, like putting, solving for your width of the tan. So let me just do that. So you have the angle being determined, but we have not determined what W is. So we need to look at that. So dA dW equals 0 previously, that would imply 2W tangent theta equals to V cosecant squared, cosecant theta divided by W squared. But theta, we already known what the value is. So tangent theta will give you 1. Cosecant theta is 1 over sine theta. So this would actually give you, so sine theta is 1 on root 2. So that gives me root 2. Okay. So what do we have? So we have 2W equals to, and we substitute V equals to W squared L. So what's V previously? Let me just go back. Okay, V is W squared L tangent theta. So this is W squared L tangent theta, but tangent theta is 1. So you have W squared L over W squared, okay, this W squared, and then your cosecant theta is square root 2. Okay. So that gives us essentially W is equals to the length divided by square root 2. Okay. So that sort of completes the that's not right. Where's the mistake? Sorry. That should be 2W. Remember that tan is essentially from here to here is W, from here to here is W, so it's actually 2W. So, well, one can solve for, so this is, okay, should read the, so when you do that, that will be L root 2, okay? So W will be L on square root 2, okay? So I think that's all one needs. So one could also measure the height if you want. The height given here is, if you recall from the earlier, the height is given by W tangent theta, but this is just simply equals to W, and W is L1. Right, okay, so I think that's it for this particular example of how to use partial derivatives to do an extremization kind of problem, or in this case it's minimization. So now what we're going to do next is the other part where we have constraints inside this particular extremization kind of problem. So here is doing extremization with constraints. So this is demonstrated through an example, which I think we need to go through it. So the idea is we have a wire bent into a curve. And the curve is given by y equals to 1 minus x squared. So what one needs is some kind of wire in this way. Sorry for the horrible diagram, but that's an inverted parabola there, okay, because of the minus sign here. And the idea is if one attach from the origin here to the curve, okay, to the wire, when are the points to be maximum, and when are the length of the, so the length here is given, sorry, something wrong. So we need the length here to I'm having problems with the notepad. Am I still with you?
Yes, doctor.
Okay, not sure what happened here, but let me just try. My pad has stopped responding. Just hang on a minute. Let me restart this thing. Okay, let me see if this works or not. Let me. Oh dear. I will have to close this whiteboard first because I don't think it detected my tablet. Just give me a minute. So let me restart that. And reopen the. Hopefully the diagram is still there. Okay, it doesn't seem to be there, but never mind. We'll do it again. So our point here, again, it's not responding. How should I do this? Sorry about this. It's back. It's good. Okay, let me just read the diagram and see. Hopefully, it doesn't give a problem again. So we have this inverted parabola thing. Oops. So there's a delay, sorry. What do I do? Let me clear the canvas. Okay, let me start fresh. So, so we have this inverted parabola, which is the parabola is made out of wire, and then we attach a string from the origin to the wire, and we try to find the maximum length. Here is given by d. D is essentially a square root of x squared plus y squared, and the wire is of this particular equation 1 minus x squared. Okay, so what we want to do is to minimize d, but this is equivalent to minimizing the square of d, and that will get rid of the square root, and that will be easier. So we okay, having problems back. minimize, let's see, there seems to be a delay. Now it comes back. So I think I'm having memory problems at the moment. So maybe I just clear that first and minimize f, which is now taken as b squared. So you get rid of the square root, and that is an equivalent problem. Okay. So and this has to be subjected to constraint y equals to 1 minus x squared. So this is the constraint. So essentially there will be three different methods. So we're going to go step by step here, and later on we summarize what's the difference between these three methods. So so the first method is by elimination. This method 1, elimination, and the second method is by implicit differentiation, and the last one is something that we're going to defer a little bit after this particular example, but it's called technique using Lagrange multipliers. Right, okay, let's do the first one. Let's do this quickly so that we get to the end of this chapter. So the first method, method 1, is to eliminate a variable. In this particular case, we eliminate y because y is given in terms of x. So let's look what happens to your function that we want to extremize here. So we have x squared plus y squared, and y squared is now given in terms of 1 minus x squared. There's a square here, sorry. And then we can expand that to be x to the 4th minus x to the square plus 1. And then you do the normal calculus thing. So you have to find the stationary points by taking the derivative and set it equals to 0. So essentially what you have here, 4x cubed minus 2x plus, well, constant will give you derivative 0, so let me get rid of that. And that would actually, if you factorize this, you can bring out x outside. That would mean, okay, let me just write it down here. So that gives you x 4x squared minus 2. Okay, so the solutions are x equals 0, and then you have another two solutions. When you equate the thing in the bracket here to be 0, that gives you x equals to plus or minus 1 on square root 2. Okay, so and if you want, we can determine which of this point gives you the minimum and which is the maximum. So what one needs to do is to calculate your second derivative. So this will actually give you 12x squared. I don't want to think too much? 12x squared minus 2, so that means it's going to be either when x equals 0, this gives you minus 2. When x equals to plus or minus 1 root 2, that gives you 4. So the negative one will give you so this is for x equals 0. The negative one will give you the maximum. And the positive one, which corresponds to this plus minus 1 root 2, gives you the minimum. So there are two minimums. So you can almost immediately see why that happens, because you have something like this. So the maximum is when you take the vertical distance here, and then the minimum will be somewhere here, for example. Okay. So that is the ordinary method. One could try to just eliminate one of the variable and then do it. The second method is the implicit differentiation. So let me do that. So method 2. So over here again, let me just write it down first. 1 minus x squared is your constraint, and your thing that you want to maximize or minimize is this squared distance. Okay, I should mention the maximum here is really a local maximum, because one could extend, for example, the length of the string over here should be more than the one, say over here. Let's draw a different color here. It could be more than the vertical distance over here. Okay, so in other words, this has to be local. Right. So what do we do? So what do we do is to essentially take differentials. Sorry for the horrible handwriting, because I'm doing it on my lap. So let's take df first. df is given by 2x dx plus 2y dy. Or in other words, one could really write in terms of df dx here, 2x plus 2y dy dx. And then the other equation that one needs to take the differential of is the one for y. So there, essentially what we do, we take dy equals to minus 2x dx. And what one can do now is to use this dy inside there. Okay, so I'm going to just the answer. Again, it's having problems again. So if you substitute dy into there, then essentially what we have is df. This implies df has to be equals to 2x minus 4xy dx. Okay. Or you write in terms of df dx, then this is essentially 2x minus 4xy. So To extremize that, then we have df dx equals 0. And that implies the following. So you get 2x minus 4xy equals 0. And then you again substitute y, and I'm not going to do all the steps here. So you get x equals 0 and x equals to plus or minus 1 on root 2 as your stationary points. And then again one can essentially find your second order derivative, which we can write it down this way from the equation here. Okay, not sure whether you can see the cursor. Let me just underline it. So from this equation you can differentiate that twice. So that would give you this. And then you can try to show that like before, which is maximum and which is minimum. Oops, not this. It's D2y. Okay. Right. What I want to do is probably, before we go to the third method, let's do another more complicated example, which is maybe I skip that. Okay, maybe not, because I want to demonstrate a few things from there. So what we do is, okay, before method 3, look at this particular example. Find shortest distance from origin to the plane given by this particular equation. Maybe I just give you the results rather than do all the whole thing. Again over here, so you extremize your distance in 3D here, and so this is subject to constraint given by this equation. So constraint, which is given by x minus 2y minus 2z equals to 3. So again, one finds stationary points. So I'm going to skip some of the working so that you can do it yourself. But here one, so this is y. So one equate this equals 0, and this gives you, let me just write down this intermediate equation. And then this implies the following: 12 plus 10y plus 8z equals 0. Then you have the other one, you have this z equals 0. So you need to do some algebra for this. We have almost a similar kind of question, but the coefficients for y and z got swapped. So, and then in order to solve for y and z, you need to solve this simultaneous linear equation. Okay? So sorry, having problems with my tab. Yeah, I think my computer is having problems now. Let me try again. Okay, let me try again. See if this. Okay. So here what we do is solve for y and z. Okay? And then one can get your x from and x obtained from the constraint. Okay? So there's some a bit of algebra going in. So and when you solve that, you'll get this solution. So your x is equals to 1/3, y and z has the same value, which is minus 2/3, and hence your squared distance will have to be the following: 1/3 squared plus minus 2/3 squared plus minus 2/3 squared. So this is your f, and that gives you equals to 1. Okay, and due to the geometry, what essentially is the problem? So you have a problem 3D here, and there will be some plane on the given in by this particular equation earlier, which is that. Okay, so that is going to be something like, okay, this is probably not the right plane, but no, essentially you have that as the plane, and then essentially you can see that, okay, the extremum in this particular case will always be the minimum, okay, because there's no the maximum distance from the origin to the plane will have to be infinite in some way, because you can have the plane extended to infinity. So in other words, from geometry, this is actually the minimum. So much of the things that we try to do will rely in a way to some geometric ideas, so that sort of you can skip some of the steps, like finding the second order derivative. Okay, from geometry, this is minimum distance. Now, okay, given that one understands that some steps can be eliminated using geometry, now let's move on to the third method. Okay. So the third method is method 3, is to use what we call Lagrange multiplier. So let's okay, we'll try to summarize first. Why do we want to get rid of why do we want to add another type of method? Because methods 1 and 2 require what we call algebraic manipulation, which can be messy. The ones that we have seen before, it's not so messy, but no, in a way, if given a particular more complicated, then it would be messy enough. So can be messy. So what do we do in this particular case? So okay, uh, you might find this a bit sort of counterintuitive in some way. So what do we do here is we have a function that we want to come on. It's having problems now. Let's see. Okay. Bear with me for a moment. So I think my computer has memory problems at the moment. Uh, Maybe we'll take a break at this stage so that I can fix my problems. So let's take a break for 5 minutes. Am I still with you or have I lost the connection? Yes, definitely my laptop is slowing down, so doesn't seem to be responsive. So we'll take a break, okay? 5 minutes. So we'll come back about 5 past 3. Sorry. Okay. Okay. I hope everyone's back. Let me just check again if I can use my whiteboard here. Close some applications. Okay. So let's just discuss this Lagrange multiplier thing. So the idea is to create an alternative method that sort of simplifies the work done for the first two methods. So what do we do? Maybe I summarize again. Method one here, what we did was to insert I in df or df dx. Okay. Method 2 was to soft define or phi. Maybe I should mention f is the thing to extremize and phi is the thing which is the constraint. Okay. Is that a question? Somebody can hear somebody chatting. Okay, so I'm not putting my camera on. So I had to mute you. Okay, so let's go back. So okay, so here what we did was to reframe this third method in such a way that we have this f to be the extremizing function. Your phi is a constraint, and what's the difference between the three methods? It's going to be this. So in the first method, we sort of put the constraint into your derivative or into your differential. Here in the second method, one actually solve for d phi to eliminate one of the variables y, and the last method is to actually multiply a constant, or really what we don't call really a constant but a variable kind of thing, to define and add to df. Okay, so this is the summary of the different methods. So let's look at that. So what's df previously? Df is going to be partial f partial x dx plus partial f partial y dy, and this is going to be extremized, so you set this to be equal 0 here, extremizing, and then your constraint. Your constraint is written in such a way that phi equals to something equals to constant. So when you take phi equals to constant, then the differential of phi is going to be equal to 0. So this will be equal to 0 due to that. Okay, and this can be written in the same way as your df. So you have d phi dx plus d phi dy dy. So you can see that the similarity between the two equations. So what do we do is to multiply this equation by lambda, and this lambda is called the Lagrange multiplier. So it seems like making the problem to be a bit more complicated, but I'll tell you why it can sort of simplify the things. So now, instead of extremizing small f, I will extremize big F, expansion of x and y, where your big F essentially is given by the small f, x and y, plus lambda times the constraint. Okay, so what one can have in this particular case, when you extremize that, one will have the following: partial f partial x plus lambda partial phi partial x dx plus partial f partial y lambda plus lambda partial phi partial y dy, and this has to be equals to 0. So the idea here is essentially you can take this, for example, and equate that to be equal to 0. So there, what happens there, you get an equation okay, I've chosen the different one, but never mind. Df dx plus lambda d phi dx equals 0, and then one can solve for lambda. So lambda is going to be given by partial f partial x divided by partial phi partial x. Okay, the idea is here you'll be able to find a value. Okay, once this value of lambda is known, one can substitute back into your capital F. Okay, so let's demonstrate this particular technique with the same example that we had earlier. Okay. Hopefully, I'm getting back this problem again. So the example here is the one before, where small f xy is your distance that you want to minimize or maximize depending on the situation. And phi xy is given by y plus x squared, giving you the curve earlier, which equals to constant here to be equals to 1. Okay, so your capital F is now what? Is f plus lambda y, so you get x squared plus y squared plus lambda y plus x squared. Okay, so you don't put the constant in. Okay, and then you take extremize of this function. Here we go again. I think the memory is not enough. So we have to clear everything. So again, is to extremize this. So you have partial f partial x, and set this to be equal to 0, and then the other one. So you better write it down first before it disappears again. So 2x plus 2 lambda x over here, and over here is going to be 2y plus lambda, and this should be equal to 0. So let's call this equation 1, and this goes to equation 2. From equation 1, what we're going to have is you will have the following equation: 2x plus times 1 plus lambda equals 0, and that will imply that x equals 0 or lambda equals to minus 1. Okay, so again, one can substitute to get your y. Y is going to be equals to 1 because your phi equals to 1. And then over here, we use equation 2 to get 2y equals to minus lambda, which is equals to plus 1. So in other words, y equals to a half. Okay, so again, one has the same solution as before. Okay, so what's the thing that we have done now was making the problem a bit more general. Okay, make the problem more general so that you introduce this Lagrange multiplier and introduce Lagrange multiplier And what happened is that by getting values, by solving for values of lambda, the algebra becomes easier. Now it doesn't really become apparent in this particular problem because the problem is quite simple. Okay, becomes easier. So we need to demonstrate this a little bit more using a different problem. Okay, so let's move on to that. Why is this solving values of lambda is going to be easier is because remember when you do this implicit differentiation thing, you normally no, if you do it for the general case, you find that you need to do some algebra to solve for things. But if you include values, then the problems get easier. Okay, so in this particular case, the problem gets, well, the calculation gets easier because you are solving for values of lambda. Okay, so again, I'm having problem with the memory again. Okay, maybe I should how much time do I have left? Still have another more than half an hour, so I think I can do it to finish it despite these problems. Okay, I'm having problem with it's not even responding to my mouse. Give me a minute just to make sure that this thing comes back. So probably I can take the attendance first. Let's see. Hopefully lost connection. Okay, I've taken your attendance, so I think that's probably it for today. I will do a separate recording so that you can watch the rest of the examples, and I will try to finish off chapter 6 in that particular video. Okay, so that's it for today. Sorry about the hiccups. Thank you, everyone.
Thank you, Dokter. Thank you, Dokter. Thank you, Dokter. Slide tu. Dah besar.